Hi everyone. This talk is about Blockene, a new blockchain architecture that enables running a blockchain on something as lightweight as a smartphone, okay, and yet scales to millions of participants at high throughput. I'm Muthian Sivathanu, and this is joint work with several of my colleagues at Microsoft Research India. Blockchains, as we know, address the problem of trustworthy transaction management. Okay, transactions could be anything; it could be financial transactions, it could be property transfers, and so on. Now, the traditional model to manage these transactions has been to use a common intermediary that everyone trusts. Okay. In the case of financial transactions, everyone trusts the bank to do the right thing. Land ownership is typically trusted with government registries and so on. Now, these intermediaries perform two key roles, right? Number one, they store the current state of the world. For example, who owns a particular piece of land today? Second, they validate transactions for integrity. So when person A transfers $1,000 to person B, the bank ensures that A at least has $1,000 in her bank account. Okay. However, there are scenarios where it's too hard or sometimes even impossible to find such a trusted intermediary. Okay. Examples are from the philanthropy ecosystem, with nonprofits and so on, public spending and so on. So that's where blockchains come in. Blockchains provide the same semantics of transaction management, but without having to trust a common intermediary. Okay. So who stores state in blockchains? All participants in the blockchain collaboratively store the current state of the world. Validation is performed by running a consensus protocol between the parties. Okay. Now, a key property that blockchains provide is that the consistency guarantees hold even if up to a fraction of the participants are malicious. For example, even if say 1/3 of the participants are actively trying to subvert the system, the remaining honest parties still have the consistency guarantees. Okay, let me start with a quick lay of the land in terms of existing blockchain architectures. Okay, broadly existing blockchains fall into two categories. The first one is public blockchains. Bitcoin is an example. These are by far the more popular of the two categories. They are primarily aimed at cryptocurrency applications, and they're designed to handle lots of participants. They can handle even millions of participants. But the downside is that they provide very low transaction throughput, often in the region of tens of transactions per second. Okay. Consortium blockchains are at the other extreme. They are aimed at business processes. So obviously they're designed to handle thousands of transactions per second, but they typically handle only a very small number of participants, 10 to 20 participants, because they run standard BFT consensus. Okay. Algorand, published in 2017, was the first one that bridged these two architectures by providing simultaneously, high transaction throughput and supporting, large scale of participation. Okay. Now, one common aspect of these three architectures is that they're all heavy on resource usage. Now, public blockchains are the worst in this category because they are based on proof of work. But even consortium blockchains and Algorand are heavy on network and storage resources for things like gossip. Okay, so they're really not feasible in the context we're talking about, namely running it on smartphones. Okay. That's where Blockene comes in addition to supporting high transaction throughput and large scale of participation, Blockene is also extremely lightweight. All it needs to run is a smartphone, and it consumes very little resources on the smartphone. Okay. So to put this architecture in context, let's look at a couple of candidate applications where Blockene is a good fit. So philanthropy is one that I alluded to a couple of slides ago. So if you look at the non-profit ecosystem, India alone receives nearly 10 billion US dollars every year in terms of donations to these nonprofits. The global number is nearly $500 billion per year. Yet there is very little transparency or accountability in terms of how these funds are managed, how much of it actually reaches the end beneficiaries, and so on. Okay, wouldn't it be great if we had a blockchain-based platform that tracks end-to-end flow of funds all the way from the donor to the end beneficiary? Okay. Another example application for something like Blockene is public spending, distribution of subsidies by the government and so on, which becomes a challenge when intermediaries or the intermediate hops through which the benefit flows can be corrupt. Okay, with that context, let's recall the three dimensions that I listed a couple of slides ago: performance, scale, and lightweight resource usage, and look at why they're important. Performance is easy. To handle real-world applications, you need high transaction throughput. Scale and lightweight cost are perhaps less obvious. So let's look into that. It turns out scale actually leads to better security. The reason for this is that blockchains fundamentally assume that 2/3 of the participants are honest. Now, when all you have are 10 participants in the blockchain, like in the case of a consortium blockchain, this property is tricky to enforce, right? It's easy to bribe, say, 5 or 6 of these participants, especially in an application like the NGO ecosystem or the nonprofit ecosystem, and defeat the whole blockchain. So ideally, you want such a blockchain to be under the shared control of millions or even tens of millions of citizens. Then it becomes much harder to do collusion attacks or bribing attacks, right? Now, lightweight sort of derives from the requirement to have large scale. Why would millions of citizens run your blockchain if it requires powerful servers and so on? So if the only way to gain widespread adoption is to make it very straightforward or almost free of cost to run a blockchain. Just with a smartphone, you should be able to do it, right? With that, let me quickly summarize the key properties that Blockene provides. It provides high performance, so excess of 1,000 transactions per second, which is quite sufficient for real-world applications. It supports large scale of participation, millions or even tens of millions of participants. It can be part of the blockchain. The key innovation, of course, is that we do this while ensuring ultra lightweight resource usage. Participants only need a smartphone. To do this, Blockene comes up with several techniques that fundamentally reduce resource usage by a couple of orders of magnitude. For example, the data usage is only about 60 megabytes per day, which is about 700 times cheaper than alternatives of doing gossip in traditional blockchains. So it's really friendly on cellular data. Only few megabytes of storage compared to alternatives, and it does this without taking too much battery as well. So the Blockene app can run almost in the background and the user won't even notice it. Okay. Let's now look into how Blockene actually works. Blockene is structured around this notion of a perfect democracy. Okay, the most important entities in a democracy are obviously the citizens. They're large in number, hundreds of millions of them. Like in the real world, most of the citizens are poor. All they can afford is a smartphone. They can't run powerful servers and so on. But because of the large number, it's safe to assume that 2/3 of them are honest. Okay. Now, all decisions in Blockene are actually taken by a majority of the citizens. For example, whether a transaction is valid, which transaction is actually going to a block, and so on. Okay. The other class of entities in Blockene are politicians. Like in the real world, politicians are powerful. They can run powerful servers, and they're largely untrusted by citizens. In fact, we assume that up to 80% of the politicians can be malicious. Okay. Unlike the real world, however, politicians don't have any voting rights on their own. All they can do is execute decisions that are taken by a majority of citizens. Okay. So given this split trust design, with citizens and politicians, let's now look at who performs the key roles that a traditional blockchain does. Okay. Now, the key property that holds in this whole system is that the only data that is trusted in the system is data that is signed by a majority of citizens. Okay. By majority, I mean a representative majority. In practice, it's a random subcommittee that's chosen for every block. Okay. So let's look at storage. Typically, participant nodes store a full copy of the blockchain, but citizens in Blockene being on a smartphone can't afford this. So in Blockene, only politicians store the full copy of the blockchain. Okay, citizens read small subsets of the data as needed to perform their role. Okay. Communication is the other key responsibility. Participants typically gossip between themselves to exchange the current state of the blockchain. But obviously, running on a smartphone, this would consume too much data usage. So this is not possible. However, citizens are the ones that are actually doing the role of performing the role of, performing validation, committing blocks, etc. So they obviously need to communicate to other citizens. So gossip in Blockene actually happens indirectly. So when a proposer, citizen, for example, wants to commit a block, they write it to a politician. Politicians gossip it among themselves, and then other citizens read from politicians. Okay, so the gossip happens indirectly. Compute is obviously something that citizens have to do. So block validation, signature validation, and so on is performed by citizens. Okay. Now I mentioned that 80% of politicians can be corrupt, right? So how do we deal with that? How do we get useful work done despite that corruption? One sort of simplifying property is that, because we only trust messages signed by a majority of citizens, politicians cannot fabricate any messages, right? So this significantly diminishes their attack vector. So I've listed a few, examples of the kinds of attacks politicians can do. They can do a staleness attack. So when a citizen asks for the latest block, they can return a previous block that was signed by a majority of citizens. They can do a forget attack. When the citizen commits a new block, they can simply drop it, not write it to the blockchain. They can do a fragment worldview attack, where a politician selectively conveys a different state to one set of citizens and something else to a different set, so they can try to thwart consensus among the citizens. So Blockene has several technical innovations that address these attacks by using several new mechanisms. For example, to handle the stateless attack, we use this notion of a verifiable replicated read, where instead of reading from a single politician, a citizen reads from what we call a safe sample of politicians. And even if 1 out of 25 politicians it speaks to says the truth, it can find out what the real state of the blockchain is. Okay. Similarly, to handle the drop attack, we always write to a safe sample so that at least one of them will actually propagate. At least one of them will be honest with a high probability. To handle gossip, gossip is tricky because we rely on the property that even if one honest politician gets a message, all honest politicians have to get that message, right? This is tricky to do in traditional gossip algorithms where you have a fixed fan out of 5 or 10 people you're talking to. So it's possible that all of them are corrupt, in which case they will just drop the data. So we have mechanisms to ensure this guarantee while consuming while not consuming too much network usage. Another challenge in Blockene is to deal with the fact that citizens are resource constrained. So a citizen cannot participate in validating every block that's committed, for example. So Blockene addresses this by vesting the responsibility of validating a block with a fixed random subcommittee of size, say 2000 citizens. So a given citizen participates in only say 1 out of 1000 blocks. Okay. Now this subcommittee is cryptographically chosen so that each block gets a different random set, and a citizen once chosen can prove to other citizens that it's indeed chosen. And this is very similar to Algorand with a couple of modifications to make it more battery friendly. Okay. One challenge that citizens have to encounter is that to validate transactions, they need to verify the current value from global state. For example, to prevent overspending, you need to know the current balance in the account. Now, how do you get this state reliably from politicians when 80% of them are corrupt is a challenge that Blockchain deals with. Interestingly, because of this fixed subcommittee for each block, this design is scalable inherently. Okay, so you can, for example, increase the number of citizens by 10x from 1 million to say 10 million, and that will only reduce the per citizen load because a given citizen will appear in the committee 10x less often. Right. The load at the politicians is also nearly constant because the size of the subcommittee that's talking to the politicians remains fixed. What happens if you increase the number of politicians? The citizen load does not increase because the citizen always talks to a fixed size random sample regardless of the total number of politicians. Similarly, the politician load also doesn't increase because during gossip with the prioritized gossip that Blockchain does, the load remains roughly constant. One important issue that most blockchains need to deal with is this notion of a Sybil attack. For example, in Blockchain, what prevents a user from spinning up hundreds or even thousands of Android VMs to get disproportionate voting power? Right. The way Blockchain addresses this is by tapping into the trusted hardware that's available in most Android phones, especially those with fingerprint auth. We ensure that every a given TE public key can have at most one active identity in Blockchain. So when validating a transaction that adds a new member into Blockchain, we check that there is no other public private key pair registered that's backed by the same TE public key. Okay. Now this can obviously be combined with other forms of identity. For example, in India we have this identity mechanism called Aadhaar, which is digitally verifiable, and Aadhaar is biometric deduped. So a given real person can have only one Aadhaar identity. So one could say that an identity in Blockchain has to have a unique TE public key and a unique Aadhaar ID, for example. Okay, let's now switch gears and discuss the prototype implementation of Blockchain. The citizen in Blockchain is implemented as an Android app. The politician is implemented as a C++ server, and we have evaluated Blockchain at scale across multiple regions in the wide area. We run Android VMs on Azure nodes for citizens, and we have the politicians node also running on Azure nodes across regions. Let's look at some performance results with Blockene. So this graph shows the transaction throughput in Blockene. So for this experiment, we ran 200 politician nodes on Azure, where each node is an 8-core VM with a network bandwidth of 40 megabytes per second. For citizen nodes, we use lighter VMs. So these are Android VMs with which are single core, 1 megabyte per second bandwidth, which is more representative of cellular data bandwidth. And both citizens or politicians are spread across 2 Azure regions, West US and East US. Okay. Now, this throughput, transaction throughput is plotted for different configurations of honesty. So the solid line at the top pertains to the fully honest configuration where all citizens and all politicians are honest. And as you can see here, this corresponds to a transaction throughput of about 1040 transactions per second. Okay. The second line is when 50% of the politicians are dishonest and 10% of the citizens are dishonest. The throughput is lower, and it's even lower when 80% of the politicians are dishonest and 25% of the citizens are dishonest. So the reduced throughput when the dishonesty fraction increases is because obviously dishonest politicians can ensure that the number of transactions read by citizens is small, so the block that's committed will have fewer transactions than ideal. Similarly, a dishonest proposer can sort of force the consensus to commit an empty block by sort of fragmenting the view across citizens. And so the key takeaway from this graph is that despite high levels of dishonesty, Blockene still makes progress. It gracefully degrades in terms of transaction throughput, right, while always ensuring safety. And the other observation here is that although this experiment is run only on 2000 citizens, we expect the performance to be the same even when there are 1 million citizens, because as we saw a few slides before, the number of citizens that are involved for a given block remains fixed regardless of the total number of participants. Okay. Let's now look at one of the key optimizations that Blockene does. This pertains to how it manages global state. So politicians are the ones that are storing the current state of the blockchain, as I mentioned. This is stored in a Merkle tree. So, for example, the latest balance in each account. Citizens need to read this from politicians, but they need to verify that this is indeed true, that the politician is not lying, right? So the naive way to do this would be to use the Merkle tree challenge path for every key value pair and actually do the verification at the citizen nodes. But this is too expensive. So Blockene has a new mechanism where most of the compute is offloaded to politicians, but citizens still ensure accuracy of the results by performing a novel spot check protocol while having guarantees about dishonesty and preventing politicians from lying about the values. So this table compares the performance difference between the naive scheme and our optimized scheme. Cumulatively across both the global state read and global state update, the naive scheme would result in spending nearly 240 seconds per block, whereas with our optimized scheme, we spend about 12 seconds. Now, this is important because our total block latency is around 90 seconds. So obviously the naive scheme would have significantly reduced our transaction throughput. In summary, we believe Blockene is the first known attempt to make blockchains work off of mobile phones, where the participants can actually participate in real consensus as first-class citizens despite running on mobile phones. And we achieve this by several novel ideas that reduce resource usage by 2 to 3 orders of magnitude, especially around network and storage. Okay, and this is enabled by a novel systems design with this notion of citizens and politicians, and we bridge the security versus performance trade-off by delegating heavy work to powerful politician nodes that are untrusted, but the citizen nodes, which are lightweight on smartphones, still ensure that politicians cannot lie and cannot affect safety and security of the blockchain. Okay, and we have detailed proofs for the safety, liveness, and fairness guarantees that Blockene provides. These are in the full version of the paper, and we believe this architecture can enable not only applications like philanthropy that we listed at the start, but a more broader class of applications where we really delegate control of state management to edge devices and therefore achieve significantly better security and resilience in the face of attacks. Thank you.